Hey everyone! Today, we're going to take a trip into the invisible world that powers literally everything around us. Seriously, we're going to build our understanding of electricity from the ground up, starting with a single tiny particle and ending with the circuits that make your phone work. Let's dive in.
So think about this for a second. What on earth connects a massive, chaotic bolt of lightning with the tiny, precise device in your hand? Well, the answer is electricity. It's the exact same fundamental force, just on a wildly different scale. And by the end of this, you're going to understand exactly how that's possible.
You know, if you want to understand a river, you have to start at the source, right? Well, for electricity, our source is something called electric charge. It's one of the most fundamental properties of matter. Everything that follows, every single spark, every circuit, all of it, it all begins right here.
To keep things simple, we're going to start with electrostatics. Now, that statics part is super important. It just means we're looking at charges that are holding still, at rest. If we can figure out the rules for when they're not moving, we'll have a rock-solid foundation for when we finally let them loose. Okay, these are the absolute, non-negotiable rules of the game. Protons are positive, electrons are negative. And just like when you play with magnets, opposites pull together, and similar charges push each other away. This simple push and pull is the engine behind everything we're going to talk about. So how strong is that push or pull exactly? Well, a physicist back in the day named Charles Augustin de Coulomb figured it all out. His rule, Coulomb's law, is basically the rulebook. And the main takeaway is this: the force between two charges gets way stronger as they get closer together.
And check this out. This diagram shows it perfectly. See that top pair? The positive and negative charges are being pulled right toward each other. Now look at the bottom two. Both are negative, so they're pushing apart, trying to get away from each other. That's Coulomb's law right there in action.
And here's what it looks like as a formula. Now, don't let the letters scare you, okay? All this really does is put a number on that push or pull we just saw. F is the force, the little q's are the charges, and R is just the distance between them. That's it. It's just a super precise way of saying what we already know.
Okay, so we know charges push and pull on each other. But how? I mean, how does one charge even know the other one is there? It's not magic. It's because every single charge actually changes the space around it, creating what we call a field of influence. We call this the electric field. The best way to think about it is like an invisible aura that every charge projects out into space. This field is what another charge feels, telling it which way to go and how hard it's going to get pushed or pulled before they even get close. Now, since this field is invisible, we draw these lines to help us visualize it. They're like a map of the force. And the rule is simple. The arrows always point in the direction a positive charge would get pushed. That's why they blast away from positive charges and suck in toward negative ones. And hey, if this whole field thing still feels a little weird, just think about gravity, right? The Earth's mass creates a gravitational field that pulls stuff in. Well, a charge creates an electric field that pushes or pulls other charges. I mean, just look at how similar those equations are. It's pretty much the same idea, just with charge instead of mass. All right, so we've got our charges, and we know they create these fields of influence. But how do we get them to actually move and do something useful for us? Well, for that, we need to create what's called a difference in potential. And this is where we bring in electric potential. But you probably know it by its more common name, voltage. All it is a measure of how much potential energy a charge is storing up, just because of where it happens to be in an electric field. The higher the voltage, the more pent-up energy it has, just waiting to be released. Honestly, this water analogy is the best way to get it. Imagine you have a big tank of water held up high. It has a ton of potential to flow down, right? The pressure is high. That's voltage. It's the electrical pressure. It's the push, that motivation, that makes charges want to move from a high-energy spot to a low-energy spot.
So once we have that push, once we have voltage, we can finally get our charges to flow in a nice controlled way. And that controlled pathway for the flow, that's what we call an electric circuit. We're getting there.
This actual flow of charges is called current, and it's super important to get this straight. If voltage is the pressure pushing the charges, current is the measure of how much charge is actually flowing past a point. We measure this flow in a unit called amps, or just amps for short. So amp isn't just some vague word for flow, it's incredibly specific. 1 amp means that 1 coulomb of charge is moving past a point in a wire every single second. And 1 coulomb is about 6.24 times quintillion of electrons. That is an unbelievable number of electrons streaming by. And here are the 3 must-have parts to make it all happen. It's like a recipe.
First, you need an energy source, like a battery, to give you the voltage. That's the push. Second, you need a path, like a wire, for the current to actually flow through. And third, you need a load, something like a light bulb, that resists the flow and uses up that energy to do useful work, like making light.
So how do all these things, the voltage, the current, and that resistance from the load, relate to each other? Well, lucky for us, there's a beautifully simple law that ties them all together. It's called Ohm's law, and it is the golden rule for pretty much everything that runs on electricity.
And there it is. Voltage equals current times resistance. V equals I times R. This one simple, totally elegant equation is the cornerstone of all circuit analysis. It tells you that if you increase the push, the voltage, the flow of current has to increase too, as long as the resistance stays the same.
This table right here just locks it all in. Let's run through it one last time. Voltage is the pressure, current is the rate of flow, and resistance is like how narrow the pipe is. And these three things are all tied together forever by that one simple rule, Ohm's law. Okay, so theory is great and all, but let's make this real. How can we actually use this powerful little law to figure out what's happening inside a real physical circuit?
All right, let's put it to the test. Let's say we have a standard 9-volt battery, and we connect it to a resistor that's 250 ohms. We want to find out what the current is. So we just rearrange Ohm's law a little bit to I equals V divided by R. We plug in our numbers, 9 volts divided by 250 ohms, and we get 0.036 amps. And boom, that's it. We just calculated the exact flow of electrons in a real circuit.
So there you have it. In just a few minutes, we've gone from a single stationary charge all the way to a complete flowing circuit that's governed by the beautiful logic of Ohm's law. You now get the fundamental building blocks of all electricity. But of course, things get more complicated. What happens when the circuits aren't just one simple loop? What happens when the road forks? Well, we'll save that for next time.